Hello, everyone. So today we're going to be taking another look at the Gibbs free energy. So in order to do this, we're going to focus in on one of our fundamental equations. Specifically, we're going to look at the fundamental equation of chemical thermodynamics. So we're going to spend the next two lectures really diving into all of the information that this provides us about real chemical systems. And one of the most important bits that it really ends up telling us is detailed information about how our free energy and thus the stability of a chemical system changes with pressure and with temperature. So let's go ahead and start by looking at this pressure aspect. So one of the first and most important things to note is that the free energy or stability of a species is going to end up the free energy of a species is always going to end up increasing with an applied pressure. And this is going to essentially vary with the volume, or if we look at a molar free energy with regards to the molar volume. Now, this actually ends up having a certain degree of logical sense. If I have a system with a small molar volume, this means that my sample is actually, quite compact. And so a little extra pressure is going to have a very small influence on the system. Whereas if I have, say, a rather spread out system, well, by packing everything in much tighter, I'm going to destabilize the system a lot more. And we can actually see this as we look through the various different phases and how they respond to pressure. So if I have a solid, this tends to have very small molar volumes. It's about as tightly packed as it can be. So if I put a whole bunch of pressure on the system, well, it's not really going to deform, or in other words, any molecular interactions don't really change with the application of additional pressure. And so you're going to have a certain amount of destabilization as you're increasing the normal force, or essentially the system's having to push back a little bit more. But I haven't inherently changed the nature of the bonds of the system that much because it's already quite tightly packed. Similarly, liquids are going to be a little bit more responsive. In most cases, liquids are going to have a slightly larger molar volume. They occupy a little bit more volume than a relevant solid because they're spending more of their time in movement, which means that their free energy is going to suffer a little bit more as they're being packed more tightly together. However, gases almost entirely rely on the fact that they don't have to interact with each other. And typically, the more you're forcing them to interact with each other, the more you're destabilizing the system. And so, thus, if you have a system that is occupying quite a large volume, if I double the pressure, well, I'm going to run into some slight issues. And we can also apply, so we're always going to find the free energy of a gas is going to suffer much more under the application of pressure than a liquid or a solid. And this is one of the reasons why under high pressures, we almost always tend to favor solids over liquids or gases because of this general stabilization. However, one of the important things to note is, well, this plot assumes that the solid is the most stable, then the liquid, then the gas. That isn't always the case. And as you've seen in everyday life, what usually most frequently dominates which of these three phases is the most stable is in fact temperature. So we need to look at how our stability is influenced with temperature. And it turns out that what we find is that as I increase the temperature, I'm going to decrease the free energy or increase the stability of the species based on the entropy of the system. And because we're looking at molar entropies and not entropies of reaction, these will always be positive values. However, we can look at the relative stabilities of solids, liquids, and gases much through this lens. So if I have a solid, well, it turns out there isn't a lot of entropy in a solid, which means that as I increase this temperature, well, I'm not actually that much increasing the favorability of the system through entropy because there isn't many more states to occupy. I've more or less occupied all of the states. So it becomes very little favored. However, a liquid, well, there's a lot more ways to organize a liquid. And as I increase the temperature, guess what? I'm taking advantage of occupying as many of those forms as possible. And so liquids are going to be much more favored over solids at high temperature, even if under normal conditions, the solid would be the favored species. Entropy is going to tend to favor liquids as I go to higher and higher temperatures. Similarly, gases have really maximized the number of possible configurations I can place the system in. So gases will always have a much higher entropy than liquids. So if I go to a sufficiently high temperature, gases tend to become the favored species. And so in general, what we're going to find is that solids with their low molar entropy are favored at low temps, liquids at intermediate, and gases at high. And we're going to spend a lot more time on this in chapter 4 as we're focusing just on phases. However, we're going to want to spend a little bit more time on some of the peculiarities of the mathematics of the temperature dependence of free energy. And next lecture, we're going to return to looking at pressure dependence. So let's go ahead and look a little bit more at this temperature dependence of free energy. So we know that it's going to have a dependence on entropy. However, a lot of times using entropy as a measure is a little bit inconvenient. So we might want to go ahead and, instead of using entropy, make use of enthalpy and free energy. So what we can do is rephrase this expression by saying, well, we know that the Gibbs is equal to the enthalpy minus the temperature times the entropy. Solve this all in terms of negative entropy. So essentially subtract enthalpy from both sides and divide by T. And we now have a new expression for negative entropy. Well, we know that negative entropy is the same as the free energy dependence with temperature. So, ta-da! This ends up actually being a little bit odd to kind of think about. But it turns out that the free energy dependence with temperature does indeed have a free energy and a temperature dependence. So we're going to see a much greater change in the free energy of a system if it's already fairly high. It's just going to be much more vulnerable to change. However, it's going to be much less vulnerable to change at high temperatures, as high temperatures more or less going to dampen out these factors. And again, we also see this enthalpic difference with, again, the stability of the system. Now, this is actually a general useful expression, and we're often going to find ourselves substituting this expression when we occasionally are dealing with matters of temperature dependence with phase properties. However, one of the other things that this is very useful is when we're looking at the second order temperature dependence on Gibbs energy. Because it turns out that a lot of thermodynamic properties actually depend on universal entropy, so the total entropy of our whole macro system, and not so much on the Gibbs. And if you remember, the universal entropy is essentially going to be related to Gibbs divided by temperature. So it's not uncommon that what we're really going to be interested in is the change of this universal entropy factor. In truth, we should have a negative factor out front, but that's easier to correct for in retrospect with temperature. And again, because it's Gibbs, we're only going to be equivalent to total entropy under isobaric conditions, because that was one of our assumptions. Now, in order to examine this dependence of the favorability, spontaneity of a system, well, we want to go ahead and deal with this messy integral, because we know that Gibbs has a temperature dependence, but we also know that temperature has a temperature dependence. So in truth, we're going to have to use the product rule, where we pull our 1 over temperature out in front, and then we deal with the derivative of free energy with respect to temperature. And then we pull the free energy out in front, and we deal with, yes, the dependence of 1 over T with T. Well, all right, that's a little bit messy, but let's go ahead and solve this in parts. So it turns out that this expression, well, we just solved on the last side. Well, that's Gibbs minus enthalpy over T. So congratulations, I managed to just annihilate any influence of the derivatives by doing a simple substitution. Well, it turns out that if you take the derivative of 1 over t, then you end up with negative t squared. And then what you end up with is a dt over t, which cancel out. So you end up with is Gibbs times negative 1 over t squared. Well, we've got a huge mess over here on this left side. So what we're going to do is we're going to we're going to distribute this 1 over t. And so what we end up with is Gibbs over t squared minus enthalpy over t squared. And then when we distribute the Gibbs, we end up with negative Gibbs over t squared. Now again, we love a lot of our thermodynamic equations because of this tendency for terms to drop out. So our two Gibbs expressions end up canceling out. And then all we're left with is the dependence of our universal entropy is going to be dependent on enthalpy and temperature. So again, if I was going to do derivative of universal entropy, there'd be a negative sign. There'd be an additional negative sign I'd have to deal with. So we'd end up with a positive on this other side. So in terms of looking at the favorable spontaneity of a system, we're going to have a dependence on the enthalpy or the stability of our bonds, or alternatively, how much heat is being released into the surroundings, and essentially the temperature, which is going to mitigate that release of heat. The higher the temperature, the less influence that release of heat has. And this second relationship is known as the Gibbs-Helmholtz relationship. And again, it's really giving us a lot of information about the favorability of reaction with its dependence on enthalpy and temperature. And so we're actually going to be making use of this expression a little bit in the next chapter, as it will help us clean up some of our equations. So next time, we're going to be focusing a little bit more on how our Gibbs free energy is going to change with pressure. Till then, take care.